Hello there, this is another lesson for Year 12 Discrete Maths. We're going to look at a graph theory, and this is the first of those, and this is the language of graph theory. So it's a bit of, I think, a boring topic, but one which is important because the questions come up in the exam all the time. We need to know it. So to start off with, for instance, this is a graph. It doesn't look like a normal graph in the normal sense of the word, but this is a graph, and all these points are called vertices. Sometimes they've got different names. Sometimes they're called nodes, but most often they're called vertices. And these are called edges. An edge is a kind of line that joins two points together. And sometimes rather than edges, they're called arcs. So I'll tend to slip in between both notations, both nodes and vertices and edges and arcs. But so this is a graph. So anything which has a bunch of vertices joined together by arcs, that's a graph. So let's have a look at things. So as I said, a vertex or node is a point. An arc or edge is a line that joins the vertices together. The two vertices are directly connected. They would be called adjacent vertices. If there is an arc with vertices at its ends. Two vertices are directly connected or adjacent if there is an arc connecting the vertices. So basically, I mean, that's a posh way of saying that if I've got a point over here, A, and I've got a point over here, B, if they are joined by an arc, then they're adjacent. If I have one which is close, but they're not joined, they are not. B and C are not adjacent. A and C are adjacent, but B and C are not. An arc that directly connects itself to itself is called a loop. Well, you might think that what's going on there, that would be a loop. And you can see, and it's basically joins it onto itself. And an indirect connection between two vertices, but it's basically where, like an indirect connection between B and C. You can see B and C are joined, but not directly. So all this is the terminology. You need to know it. So let's have a look at this question here. What is it? How many vertices does this graph have? Well, straight away look at that. There's 5 vertices. List the 5 arcs in the graph. Well, you've got AB. I can see you've got AC. You've got you've got BC. That's the one I wanted to say. But you've also got AD. And you've also got BE. I mean, that's easy enough, isn't it? So just 2 letters will do the job for us. Which vertices are adjacent to C? Well, which ones are joined directly? Well, A and B. A, comma, B. And write down the indirect connection between D and E. Well, you go D to A to B to E, something like that. You can see they're joined. Got some answers, and that's what I've got in my answers as well. All the others, I'm sure, are correct. Graph theory, there's some more terminology and notation. A graph is connected if you can basically get from any vertex to any other. So this is a connected vertex or a series of vertices. So that's a connected graph. Whereas this, I'm going to put my vertices in exactly the same point. But if I just join them up like that, you can see I've got effectively there's a gap in between. So this is not connected. This is connected, this is not. Simple is if you only have one arc connecting a pair of vertices together. So this is simple. If I was to draw that and have a second way of going from one place to another, you can see I've got one way, I've got a second way. Now this is not simple. So if you have 2 arcs basically going from one place to another place, then that is not simple. And the graph that is both simple and connected is said to be simply connected. Well, that's obvious. But the important thing, you understand what simple means, you understand what connected means. Now, the bit that's a bit less obvious is the degree of a vertex. So on my picture over here, the degree of this one is 1, 2, 3. 3 arcs coming out of it. That's basically what the degree is. It tells us how many come out of it. 1, 2, 3. This one's 3. This one here is, well, that's 1. 1, 2, 3. That one's 3 as well. So on this one, it's 3, 3, 3, 1. And you very often write them down like that. So here's the same graph. What is the degree of each vertex? Well, 1, 2, 3. This is another 3. This one's a 2. 1, 2, 3. This is a 1, and this is a 1. Okay, that's easy enough. Work out the sum of the vertex degrees. The sum is obviously where you add them up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there is a link here, by the way, and this link is actually being asked about in question C. Why is the sum of the vertex degrees twice the number of arcs? You'll notice I've got 1 arc, 2 arcs, 3 arcs, 4 arcs, 5 arcs. So there are 5 arcs, and the sum that we just calculated was 10. So this is what they mean by they're saying it's twice as big. And it's basically because whenever you draw an arc, there's 2 ends to it. There's this end and there's this end. And that will count twice in the vertex degrees. So if we have a look at the answers, we've got, well, I'd already said what the vertex degrees were. They did add 10, and each arc has 2 ends. And I'm sure if you read that, it all makes sense to you. So we'll keep flying through this at a fair rate of knots. A few things for us to note. This is the rule that we were just talking about. The sum of the vertex degrees is twice the number of arcs. You should write that down because that's an important rule. And the consequence of this then is it says you cannot have an odd number of vertices with odd degrees, because if you did have that, effectively your total would end up to be odd. So you can't have an odd number of odds. And by an odd vertex, I basically mean, so again, drawing my random picture. So if I'm going to join this up in some way, so this is 1. That's an odd vertex. 1, 2, 3. This is odd again. This is it's got 3. This one is what? This one's 2, and this one's 2. You'll notice I've ended up with 2 odds. You can never end up with an odd number of odds. And here's a first definition of what we mean by a tree. A tree has n-1 arcs if it has n vertices. Now, an example of a tree would be something like this. You can almost imagine this being in probability when you was doing this at GCSE and you were doing tree diagrams. A tree looks something like this. It doesn't have to be like that. It could have, say, 3 branches coming off. But you'll notice whatever I've just done there, and that's a dot there as well. So how many vertices or dots do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10 vertices. And so by this rule, I should have n-1 arcs. I should have 9 arcs. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. There you go. Ding! It did work. And I've just got underneath all this, I've just got this a tree is a connected graph with no circuit. So this is another rule that we just need to be aware of. That if you ever have a loop, I've called it a circuit on this, but you could easily call it a loop as well. If you ever have a loop, then it can't be a tree. And because if you do, you break your rule that basically says you can only have n-1 arcs. So you'll notice there's no loops here. There's 1, 2, 3, 4, 5. 5 vertices, all right, v equals 5, and arcs 1, 2, 3, 4. What about this one? 1, 2, 3, 4, 5. Again, it's 5 vertices, and arcs, you can see 1, 2, 3, 4. So same idea, but just new examples. So there are 2 different trees, it says, with 4 vertices. So I'm just going to start off with 4 vertices. Now I suppose you could draw it down there, and that would be the equivalent, if you just realize the way I've drawn that, is it would be the equivalent of just drawing a straight line. Those 2 things are the same. You can see it just basically a long line. Or I suppose you could, instead of that, draw one which is this like that, and rather than me drawing it on there, I could have joined it on there instead. And this then, I suppose if I draw this slightly better, I wouldn't have bothered with all this one. They are my two answers. Get my pen back. And so it says list the set of vertex degrees for each tree. Well, here I've got a 1, I've got another 1, I've got another 1, I've got a 3. So this is a 1, 1, 1, 3. It doesn't matter how you list it, but you can see the logic of putting them in some kind of order. This is a 1, a 2, a 2 and a 1. And again, 1, 1, 2, 2. Does it really matter how they're listed? Probably not. Let's see what I've got. And in fact, that's almost identical to what I've just done. Terminology again, more and more terminology for graphs. A subgraph is formed by basically having part of a graph. That seems reasonable. A walk is a connected subgraph consisting of a set of arcs where the end vertex of one arc is the start vertex of the next. Well, you basically means you're just going round and you keep going round. Some of these terms you'll soon realize. So that would be a walk. A trail is a walk in which no arcs are repeated. Well, mine would also be a trail. This is a walk, but it's also a trail. A path is a trail in which no vertex is repeated. You could imagine going through on a walk then where you don't, on a walk or a trail where you don't go through. For instance, that could still be going through here and then over to there. That would be both a walk and a trail because I'm not repeating the arcs, but it wouldn't be a path because I've gone through this same vertex. A cycle is a closed path where basically you end up where you started. And a route is any of them. It could be any of them. So just bear that in mind. You get words which kind of mean something in English, but might mean something different in normal routines and stuff. So on my first diagram here, I've got ZW, XYW. I'm just trying to think what that is. Z to W to X, Y. No, have I done that wrong? Z to W to X to Y to W, I see. And that is a trail because no arcs are repeated. I don't go back to where I started. So that is a trail. But if you look at that, it can't be a cycle because it's not. You don't go back to where you started. So a path. I did go through the W twice, so it can't be a path. So you can see it's almost like a hierarchy here. The next one, if I just rub all that out. So I didn't want to do that. Let's try erase it this time. Yeah, there it is. So if I just try to draw this next one, then we can see it ZW from Z to W to X to Y to W to Z. So we get back to where we started, but it's not a trail. And that's because I've gone down WZ twice. So it can't be a trail. And are we on the same things? X, Y, W, Z. X, Y, W, Z. All right. So I think that is that one. X, Y, W, Z. And they're saying that is a path. Okay, reasonable. And the next one is W. Oh, sorry, so Y. Let's get rid of all those. Oh, we didn't want that. And what have we got? We've got. It's just getting your head around, isn't it? Y. I'm starting at Y. I'm going to go to W. And I'm going to go to Z. And then I'm going to go to Y. So straight away, I know it can't be a path because I've repeated the same vertex. That's really what it's saying. And I actually then carry on. I go back to X. Or I even go up to X even. So trying to get our head around it is what this is about. Let's do this one. It says ABCA. ABCA. You can see that has a little loop. So we're calling that here a cycle. And the next one is D. So again, I'm going to rub that out just so that I can get my head around the root. And it says DC to B to A to D. It's a cycle. Yeah, seems reasonable. Notice in a cycle, you are allowed for the first and your last vertex to be the same because otherwise you're not going to end up in the same place. So here are two more examples to illustrate the connected, not connected idea. And I think it shows it very easily, very well. So this is a connected graph. You can see all the vertices somehow are connected to all the other vertices. This is a non-connected graph because there's a gap in between. It's in two parts. Now, I have seen questions which asked us to draw say some like a graph with so many arcs and so many vertices, and the only possible way of drawing it was to draw a non-connected part, sort of version of it. And I remember been thinking about this for weeks and weeks, and not well, a couple of minutes, and I was trying to work out how this could possibly be. I don't know what it was, 4 arcs and you know, uh, 3 vertices or whatever it was. I can't remember exactly what it was, but it was impossible to draw unless you went down this route of doing it in 2 separate parts. And once I sussed it, it was like, ah, dear. So just the mere fact I'm highlighting this is because it occasionally comes up. And then the second type of graph, which is linked to this, is simple graphs. So a simple graph, if you remember, has got 2 vertices only ever joined by 1 arc at a maximum. And so here you can see, like, yeah, it doesn't have to be A and D aren't directly joined, but all the ones that are joined and connected, it does so with only 1 arc. Whereas this one is not simple, because between U and W, there's 2 ways of getting directly from one to another. And there's other ways of going non-directly, but that doesn't matter. It's the simple bit. So this would be called a simple connected graph, because you can see it's all joined together. This would be non-simple, but it is connected, but it's non-simple. Okay, let's keep moving on. And now complete graphs. These are important, and they come up more often than you'd think. A complete graph is a graph where all the vertices are joined by as many arcs as possible, kind of thing. So for instance, here you've got 4 vertices. So from each vertex, I've got to join all the others. Well, I missed, but you get the idea. So that's got 3. Now this one is already connected to there. So this one will need 2. And now I come to here, they only need to go up. And that actually is as many as you can get. You can see all of these are going to be connected. So interestingly, to do that, I did 3 for the first vertex, then I did 2, and then I did 1. So there was a total there, I think 1, 2, 3, 4, 5, 6. But interestingly, one way of thinking of this was 3 for the first vertex, then 2, then 1, and the last one actually didn't need any because that was already now joined. So it's a similar trick on this one. If I draw here, you'll notice for the first one there are going to be 4, and you'll notice 4 because it's K5. So it's a 4 for that one. And then from if any one now, I don't need to draw there, you see. It's already connected. So 1, 2, 3. So that's plus another 3. And then if I do from here, I need 1, 2. And from this one, I just need the 1. And that's me done. So here it's 10. Now you might start thinking about a rule for this, because these are actually what are known as the triangular numbers. Triangular numbers are where you add up all the numbers up to a certain point. So the first one here for a K6 graph needed 5. And it won't surprise you when I eventually do this. I'm going to get 5 plus 4 plus 3 plus 2 plus 1. Here's going to be the 4. Here's going to be the 3. Here's going to be the 2. And here's going to be the 1. And the last one doesn't need any at all. And so there I've got 15. So that's, I think, interesting in itself. There is a formula for this. It comes up down here. Well, the formula for the triangular numbers very often is written n plus 1 over 2. But you'll notice in this example, it wasn't 4 that mattered, it was 3 plus 2 plus 1. So we have to slightly adjust that formula for the triangular numbers. And I'll do so now. And you'll see it's very similar. But because we've already taken 1 off just to start, it becomes n times by effectively n minus 1 over 2. And so on this first one, when there is 4, what are we doing there? It's 4 times 3 divided by 2 is 12. And this formula then will work for these. So it's a slight adjustment on the triangular numbers formula. Write down the numbers then in K5, K6, K7. Well, K5, well, I've written that down as 10. K6 is 15. The next one, if I do it, will be 7 times by 6 divided by 2, which is 21. If you added 6 onto there, you would get that. Um, the question one here, which I didn't do, K4 is in fact a planar graph. Yes, it is. Doesn't look very plain. A planar, if you're not yet aware, is where a graph kind of doesn't cross over in this bad way. Like this looks like it's crossed, but there's no vertices there. I've not put a dot there. So how could I demonstrate this? Well, I could draw my 4 outside ones. I could draw that one down to there. And with this one, rather than going across there and be a bit lazy, you can just draw it around the outside. And that demonstrates that you can do this in what's called a planar graph. Now, we'll come back to planar graphs soon, and particularly in year 13 discrete maths. We learn a lot about whether a graph is planar or not planar. But that's our first look at this idea of planar graphs. An extension of this then, like a lot of their work on discrete maths came from a mathematician called Leonhard Euler, and this is his name here. Now it says there he's a Swiss mathematician, and this idea of well, Euler was a fantastic mathematician, but this idea of discrete maths, he really invented a lot of it. And so if we look at this, this was what is a town or a city called Königsberg. Now, it's not actually called Königsberg now. It's actually now part of Russia, and it's called Kaliningrad. I think I've spelled that Kaliningrad, something like that. But it's a little part of Russia, which is just underneath the Baltic states of Estonia, Latvia and Lithuania. And it sits bordering Poland. And I think a long time ago it was part of Poland, perhaps. But the idea was the people of Königsberg, or now Kaliningrad, used to, it was before TV, remember this, before playing video games, before being able to do a lot of stuff. So they used to go for a walk on a Sunday, or whatever day it was, and they used to try to walk around the town and all the bridges on the town without having to cross the same bridge twice. So and finish up where they started as well. So you can imagine someone living here going across this bridge, going, all right, yeah, I've got this. I'm going to do this. I'm going to cross over there. Oh, I can't now get over here. Well, I can, but I'd have to cross this bridge again. And, that was, you weren't allowed to do that according to the rules of the Königsberg game, if you like. And this went on for a long time. And a lot of people, said you could do it. A lot of people said you couldn't do it. And I suppose Euler must have lived there for a time or knew about this problem. He basically went away and thought of a way to prove that this was impossible. And he eventually proved it was impossible. And he did this by considering the areas of all this area up here as being a point, a vertex. So that might have been A. And then the bridges were the arcs. So you'll notice to go from, I'm going to call it A to B, there are 2 ways of going. Actually, I've mislabeled that, A to D, according to my picture. And likewise, down to C down here, there are 2 ways to do it. So you can see the logic of this, the logic of Euler's. And Euler's brilliance was to say, well, I can just draw this in terms of vertices and arcs, and you can see the way that goes. So that must be B over here and round to there. But he drew it as this, and he looked at the orders, and then order is, I should tell you, we've already come across this word, degree. Order and degree then are the same idea, and lots of times in this topic we'll see the same word used twice. And so he looked at the degree of each one, and so you'll notice here the degree of this vertex is 1, 2, 3, and this one is 1, 2, 3, 4, 5. And this one is 1, 2, 3, and this one is 3. So I'm just going to write this in here. So 3, B was 3, C was 3, and D was 5. And this knowledge was enough for Euler to go, therefore we've proven that it's impossible. Now, for the rest of us, perhaps that's not enough, but this is what he found out. Euler found out that the number of odd vertices mattered. Now, I've already talked about odd vertices. All 4 of these are odd numbers. So we got 4 odds. Euler found out if you had no odds, then you could basically walk around this. If you had 2 odds, you could, but you would end up in a different place to where you started, which may not be ideal. But if you had 4 or more odd vertices, then you weren't going to be able to do it at all. And this is what Euler found out. And this is the rules that we're going to use. So look out for this in exercise 2b, and the video for exercise 2b. So in the meantime, we'll look at exercise 2a in class. Thank you very much.